Hey everyone, so I wanted to do another video where we're going to find the basis for the kernel and the range of a linear transformation. I've done a similar video where we found the basis of the null space, column space, and the row space. And the kernel and the range of a linear transformation are very, very related, similar concepts, just looking at them through a different lens. So I wanted to take a look at an example where we do this. And in this question, we're given this vector x1, x2, which is clearly a vector in R2, and we're given this linear transformation L, and it goes from the domain of R2, transforms it into a vector in the vector space R3, which is our codomain. And it's defined for us in this way here, where it's each of the components of our vector in R3 is just made up of some sort of addition, subtraction, or scalar multiplication of the individual components of the vector that goes into our domain. So find the standard matrix L of the linear transformation. So finding the standard matrix that describes this linear transformation, if the linear transformation's already been defined for you, this makes our life a whole lot easier, because all we need to do for this is to plug in the standard basis vectors of the domain into our linear transformation, and this will make up the columns of our standard matrix. So let's begin by doing that. So starting with the linear transformation of, and remember the standard basis is given by these like elementary vector lowercase e sub 1, and I'm also just going to write this out for clarity. I'll write this in the vector form as well, but E1 would be the exact same thing. So you might also see this as like 1, 0, like this. These all are meaning the same thing, they're just different notation. And since it's defined, we know that, well, the first element is 1 minus 0, the second element is 1 plus 0, and the last element will be 2 times 1. So this is going to give us the vector in R3, 1, 1, 2, right? And I've written it in that form that it's given us, but if you prefer this square bracket notation, writing it like the transpose, nothing wrong with this. If this makes more sense, I would just go with this. So this is what the first standard basis vector of the domain maps to, of this linear transformation. Okay, let's do the exact same thing now with the second standard basis vector, right? And this is like 0, 1. Okay, this is going to be 0 minus 1, this is going to be 0 plus 1, and it's going to be 2 times 0. So lastly, we are going to get negative 1, 1, and 0, or negative 1, 1, 0, written this way. Same thing. I've clearly written out a lot of different notations here, but in general, you just stick to the one that you want. And yeah, I mean, typically, if you're comfortable with all of them, stick to the same notation as that's given in the question. Okay, and let's scroll down here. Okay, and remember, the standard matrix that describes our linear transformation, well, the first column is just going to be L of E1. Second column will be L of E2. So we know that this will be 1, 1, 2, and our second column will be negative 1, 1, 0. Okay, so this is the matrix that describes our linear transformation. So next, this is asking us to find a basis for the kernel of L and the range of L. So let's do a little bit of a refresher of what these actually mean. Well, we know that the kernel of L is just going to be, it's all remember our linear transformation can be expressed as this standard matrix L times a vector x, and when this is equal to the 0 vector, well, the kernel is going to be all of the vectors x that, when multiplied by our standard matrix L, will map to the 0 vector of our codomain, right? So another way that you might see this written in like a textbook is like if we take the linear transformation of a vector x and it's equal to the 0 vector, right? You'd probably see it just described like this. And it's the exact same thing. It's just when I first wrote it, I wrote it in terms of this matrix vector product of our standard matrix L times a vector x is equal to the 0 vector in R3. Except you can see it's a lot neater when you just write it as linear transformation of x is equal to 0, right? So same thing, but you'll notice that this is like by definition the null space. If we had like ax equals 0, right? Some matrix vector product ax equals 0. Well, all of the vectors x that satisfy that equation will be the null space, right? So you can see how these are very, very related concepts. And we can see how if this is just the null space, then we should solve it pretty much the same way. We just need to set up a matrix of our homogeneous system, L times x equals 0 vector, row reduce this, and then we'll interpret the results from there. So let's set up a matrix, right? So we already did or found what our matrix was, our standard matrix. It was this 3x2 matrix right here. So now let's row reduce this, and I'll go through this somewhat quickly. So let's do R3 is going to be equal to R3 minus 2 times row 2. So this will be 0, this will be minus 2, this will stay the same, and then we can do row 2 is going to be equal to row 2 minus row 1, just trying to get rid of the non-zero entries underneath the top left entry of this matrix. All right. Next, we're going to try to get rid of that bottom right entry. So we can do row 3 would be equal to row 3, and we're going to add row 2 to it. And then lastly, let's just we'll divide row 2 by 2. And we'll be left with 1, 0, 0, negative 1, 1, 0. And we can see now that we are in row echelon form. And from the row echelon form, well, we can see that since that there's no free variables here, right? Or the rank of this matrix is equal to the number of columns that we have. Well, we can see that the only solutions to our homogeneous system would be the 0 vector, right? And if that's not entirely clear, then let's look here. Like we've got, remember, like this first column, if we're solving this matrix vector product, L times, let's write this as x1, x2, this is equal to 0, 0, 0. Then the solutions to this system, remember we're solving for, I get this x vector, right? And you can see here, right, like this first column and the second column of our reduced or of our row echelon form, we can see that those kind of like represent the components x1 and x2 of the system of the solutions that we're solving for, right? All of the vectors x that satisfy this homogeneous system, this matrix vector product, right? So we can see that since there's no free variables, x1 and x2, they have to be equal to 0, right? The 0 vector is the only solution to this matrix vector product, right? So if x equals the 0 vector is the only solution, then that means that the kernel of the linear transformation only consists of the 0 vector, right? So we can write this as, well, the kernel of L is equal to, and remember, this is a set of vectors, but it's equal to the set of vectors, which only contains the 0 vector. And if you're asked about the basis of the kernel, it's not asking you for the kernel, it's asking you for the basis. Well, careful here, you know that if a set of vectors only consists of the 0 vector, then it follows that the basis of that set of vectors would be the empty set, which is basically just the set of nothing. And it's a little bit confusing. I probably can't explain it as well as some other sources that you might find online. So just remember that the set of the 0 vector, the basis for that set is the empty set. And you can denote that as just this symbol right here, like this. So we can say, thus, the basis for the kernel of L is the empty set and here we are. And sorry if this video is a little choppy, my internet connection is being kind of dodgy. So we've answered the first part of the question, right? But we're also asked about the range of L and the basis for the range of L. And we were talking earlier about how kernel and range are very hand in hand with the null space and the column space of a matrix. So the range of L, well, the range of L is all of the possible outputs of this linear transformation, right? So L of x, it's like every single L of x, right? What this could be equal to. So if you plug in some vector x into this linear transformation, it's going to spit out some vectors in R2 or R3, sorry. So the set of all of those possibilities is going to be the range of L, right? And you can see how that's super duper similar to the column space, right? So if we wrote this as standard matrix L times some vector x, right? Let's write this a little bit differently, x1, x2. Well, it'll be x1 by definition of matrix vector product, right? It's going to be the first column of L, which is going to be 1, 1, 2, 1, 1, 2, plus x2 times, well, the second column of this standard matrix L we found was negative 1, 1, 0, right? And this is for some x1, x2, which are just some scalars, right? Because we're considering all possible x vectors x in R2, right? So can you see here that if we replaced these x's with like scalars like c1 and c2, you can see very clearly that this is the column space, right? This is the span of the columns. This is the span of the columns of L, right? So you would solve it the exact same way that you would solve for the column space of some vector. So the range of a linear transformation L, you can see, is super similar to just the column space of that standard matrix L that describes the linear transformation. So since we've already solved the this homogeneous matrix, or the homogeneous system, right here, we solve it the exact same way. Since we saw that x1 and x2, they have to be equal to 0, or there's no free variables, we know that the span is going to be it's going to be the columns of our standard matrix L. We have no free variables, so we can't remove any vectors from the span of the columns and have it span the same vector space. We can see that since there's no free variables, it means that the span of the columns, we can't remove anything from there, and they'll span the same thing. So it's simply just going to be the span of the columns of our initial standard matrix, standard matrix L. So we can see, let me just write out in words what I just said. We see from the reduced echelon form of our standard matrix L, we have a leading entry in column 1 and column 2. Thus, we can say that the range of L is going to be equal to the span of column 1 and column 2. And now, considering the basis of the range, well, we can see that since our vectors here, 1, 1, and 2, and 1, negative 1, 0, well, since that these are both non-zero vectors and they're both non-parallel, we can see very clearly that they're not scalar multiples of each other. We can see that these vectors form a linearly independent set, right? And since they form a linearly independent set and they span the entire range of L, then that means that we can take the set of those two vectors and call that the basis for our range. So I've just written out exactly what we just said. So to recap this video, we were starting off given a linear transformation and it was defined for us. We were then asked to find the standard matrix of the linear transformation, and we did that by plugging in the standard matrix vectors of the domain and finding out what those vectors map to. Those vectors become the columns of our standard matrix. Once we found that, we needed to find the basis for the kernel and the range. So we started off by finding the kernel and the range, and then we interpreted our results to find the basis. The kernel was just all of the vectors that, if you were to plug in to the linear transformation L, they would map to the 0 vector. We saw that this is very, very similar to the null space, and we solved our homogeneous system, and we found that the 0 vector is the only vector that exists that maps to the origin of our codomain. Thus, the basis for the kernel, since the kernel only exists of that one 0 vector, then the basis for this set will have to be the empty set. We also saw that the range of L is very similar to the column space of the standard matrix L. So we saw that since we have a leading entry in both column 1 and column 2 and no free variables, we can take that the span of just the columns of our standard matrix L is going to be equal to the range of L, and it can't be simplified in any way. So we notice that since that those vectors are non-zero and non-parallel, they'll form a linearly independent set, and since they span the entire vector space, which is the range of L, then we can call the set of those two vectors the basis for the range. I hope this video was explained well. If you have any questions, then please drop a comment and I'll do my best to answer them. Great. All right, have a good day.